you've put the link. Hey, thanks. So yeah, I'll start with my talk now. The talk is on lower bounds for convex optimization. And this was joint work that I did with Ankit, Robin, and Praneeth when we were at Microsoft Research in Bangalore. And to start with, let's just take a look at what convex optimization really is. So the task of optimization in general is quite simple to state. You have an unknown function that takes in n real numbers and outputs one real number. And you want to minimize this function in some region, which we'll assume to be the unit ball for the purposes of this talk. And so to formally state that, we want to find an input point x in this region, such that your function value at this input point is close to the minimum. It need not be exactly the minimum possible, but it's at most epsilon more than that. So we'll call such points epsilon optimal points. And this task, I mean, if the function is really unknown, you can't really output such a point. So you should be able to learn about the function somehow, and that is given to you via an oracle. So I'll be more precise as to what the oracle is, but for now, just think of it as some machine to which you can give an input x, and it'll output to you f of x or some related information about f at the point x. Unfortunately, even with this oracle, you still might need infinitely many queries because there might be a single point where f takes a really small value. So we need an additional promise that f is at least continuous. And so we generally make the assumption that f is not only continuous, but is Lipschitz. So it's here L0 Lipschitz means that L0 is a real number. And that's also the maximum slope that you can have at any point in any direction. So with this additional assumption that f is now L0 Lipschitz, we actually do have an algorithm which solves this task. You can just take an epsilon divided by L0 net of the unit ball, and one of those points should be epsilon optimal. That's easy to show. Now, we're going to look at different promises. So convex optimization is basically adding extra promises about the function f. But first, let's look at a very well-known algorithm that works in this framework. And that's the gradient descent algorithm, which is used a lot in machine learning, especially when you have neural networks. So in such models, you have lots of parameters that you have to set. And based on these parameters, the neural network has some behavior. And you want it to solve some problem that you have, and you're measuring how much error it makes when solving it. That's the loss. So you're looking for what parameters should I set such that my neural network's loss is minimized. And the way gradient descent works is it looks at the loss that's computed, it looks at the gradient of the loss function, and it decides what parameters it should try next. So it's very much a query algorithm where it's querying a set of parameters. It's seeing the output of how much loss that these parameters incur and what the gradient is at that point of the loss function. And then it makes another query. It gives a different set of parameters. And it's used when you have like many parameters, and there is some theoretical backing for this. And to see why, we can look at this very nice guarantee that gradient descent has. If you're promised that f is convex, and the oracle that you have gives you not just the function value, but also the gradient of f, then gradient descent requires only L0 by epsilon square queries in order to find an epsilon optimal point. And this is quite impressive because this is dimension independent. Even if you just fix epsilon to be, say, 1 by 100, this is basically 10,000 queries, assuming L0 is 1. And it doesn't matter how many parameters you have. Even if you have like a trillion parameters, you still need only 10,000 queries in order to epsilon optimize your function. And we can look at how gradient descent works. I've kept some slides for that. I've kept it at the end of the talk in case anybody wants to see how it gets such a guarantee. But in the talk, mostly I'll be talking about lower bounds, so that won't actually be relevant. If you want to see it, you can let me know. So for now, what I want to say about gradient descent is that it's known to be optimal among deterministic and even randomized algorithms for decades now. So it's a very good dimension independent algorithm, and you can't do better with deterministic or randomized algorithms. Now, before I continue and talk more about the complexity of this task, let's just make a few observations about this task. So the complexity of an algorithm could depend on quite a few parameters. There's the dimension of the space, n. There's the epsilon, which is your optimality parameter. There's the promise that you have on the Lipschitzness of the function. And we assumed we were optimizing in a ball of radius 1, but it could in general be a ball of radius r. So there are these 4 parameters that the complexity of this task could depend on. But in general, you can always assume that your radius is 1. So that is the question of optimizing with these 4 parameters is equivalent to the task of optimizing with these new 4 parameters where the radius is 1 and the Lipschitzness guarantee has gone up. And that's because basically if you're optimizing f within a ball of radius r, it's the same as optimizing a function f prime in a ball of radius 1. And f prime can be, you can simulate queries to f prime if you have queries to f. It's very straightforward. And so now optimizing f prime is a function in the latter problem type. So we're assuming radius is 1, and it only depends on the other 3 parameters really. Now, it turns out that you can also set the Lipschitzness constant to 1. So if you're asked to optimize in the unit ball with the promise that your function is L0 Lipschitz, then you can also optimize a different function f prime, which is f of x divided by L0. So f prime now has Lipschitzness guarantee of 1, but now you have to optimize it to within a precision of epsilon by L0, because the set of points that are epsilon optimal for f are the same as the set of points that are epsilon by L0 optimal for f prime. So all this just to say that even though there are 4 parameters here, we can assume that the last 2 are set to 1, and the dependence of this, the complexity's dependence on n and epsilon completely characterize the complexity of the algorithm with respect to all 4 parameters. Now, if that didn't make much sense, it's fine, but I'm just justifying the fact that from now on, I'm going to be assuming that R and L0 are both equal to 1. So now let's look at this, what we know about this complexity. So in this graph, we've fixed epsilon. So say, epsilon is equal to say 1 by 100 or something like that. And we're looking as we increase n, how does the complexity of this task change? So we know that if n is equal to 1, that means that you're optimizing along just the interval -1 to 1, and you can use binary search. And if you just binary search through this to find the minimum of your convex function, it'll take only log of 1 by epsilon steps. So when n is equal to 1, there's a very quick way to do it, and that's just binary search. And that method actually generalizes using a much more complicated algorithm called the center of gravity method. And that guarantees that in dimension n, you can find an epsilon optimal point in order n log 1 by epsilon steps. So if n is smaller than 1 by epsilon square, center of gravity method gives you a better guarantee than gradient descent. And if n is larger than 1 by epsilon square, gradient descent gives you a better guarantee than center of gravity. And the question is, are these algorithms optimal? Can you actually do better than these? Like this whole region, can I get a better lower bound somewhere inside this region? A better upper bound, sorry. And the answer to that is no. If you're looking at deterministic algorithms, this complete envelope is tight. These are the best algorithms that exist. And this has been known since the 80s. In the randomized setting, we knew that all of these were still tight up to a log factor. And in fact, they are tight up to constants, but that was shown much more recently. So it was known from the 80s that when n is larger than 1 by epsilon to the 20, then randomized algorithms are, then gradient descent is tight up to a constant. And much more recently, it was shown that when n is larger than 1 by epsilon to the 4 itself, that it becomes tight up to a constant. And in a recent paper, we showed that, in fact, as soon as gradient descent becomes the better algorithm, it is tight up to a constant. But this is not the result I really want to talk about. The question that we have is, what about quantum? What's the quantum complexity of this task? And this was posed explicitly by this paper, Chakrabarty, Childs, Lee, and Wu. Now, they had studied the complexity of this task when the oracle only provides you f of x. It doesn't provide you the gradient of f. And in their study, they noted that computing the gradient of f from just queries to f is hard classically, but it is actually easy for quantum algorithms using something similar to Bernstein-Vazirani. And they weren't the only person to have used this or studied this, but they were the people to have posed the question, what is the complexity when you're also allowed access to the gradient? Now, this is an interesting question because there is something known as the cheap gradient principle, which says that it's like a white box simulation. So if you have a reasonable algorithm for f, if it's implemented in some sort of arithmetic circuit or something like that, then you can give an algorithm for the gradient of f that also runs in around the same time. So it's not really fair to just say that you have black box access to f, but you're not going to get access to the gradient of f. You should also be giving the access to the gradient of f, because in reality, you can really find out the gradients yourself. And so in this setting, we're going to look at an oracle. So this is now the quantum model. So the model is quite similar to that of just normal quantum query complexity. You have an input register, which has as its basis states input points, x in R to the n. So there's a question of what precision you want, which I'll come to in a bit. But the general thing is that you have an input register where you have inputs that you can give. And there's an output register, which let's assume A is some basis state for the output register. Now, when you apply the oracle for f on this state, all it does is it changes the output register in a reversible way to also give you the value of the function f of x and the value of the gradient of f at x. Now, with infinite precision, I'm not sure what the mathematical model would be. Nevertheless, with whatever precision you choose, our lower bound should still work. The only thing our lower bound actually asks of the query model is that if you have two functions, f and f prime, such that they have the exact same behavior at some input point x. So that's here we have this is f's behavior at some input point x, this is f prime's behavior at some input point x. Then if I take any state in which the input register just corresponds to that point x, then when you apply the oracle for f or the oracle for f prime, you should get the exact same output state. That's what we'll require of our query model. And this is a very reasonable requirement for any model that claims to be a black box model. Right? Yeah, so if there are any questions about the model or
can I ask about the cheap gradient principle, Suhail?
yes.
So nabla of f is a much bigger object than f itself, right? Like the value of f is one real number, but the gradient is n real numbers.
That is true.
So
yes.
when you say that they run in around the same time, do you mean like up to polynomial factors in n, or do you really mean around the same time?
So I've seen the abstract of these papers. I haven't really gone through the results themselves, but they say that they run in 6 times the time complexity of f.
Oh, really? Okay,
yeah.
That's
so
impressive.
Yeah, I'm not.
And
if
really
f ignores most of
output,
its inputs, that shouldn't be possible, but I don't know what.
They literally output an n-dimensional vector, which is the gradient then?
That's what it sounded like, yeah.
Okay, thanks.
Yeah. All right, so what do we show about the quantum complexity of this task? Well, it was implicit in the paper of Chakrabarty, Childesley, and one of the lower bounds that they had given in a different setting implied a lower bound of 1 by epsilon for our setting also of non-smooth convex optimization. And so this is the lower bounds that were implied from their paper. According to this, it's still possible that you have a quadratic speedup for dimension independent complexity of non-smooth convex optimization. But what we showed was that, in fact, you cannot get a quadratic speedup. You can at best, gradient descent is still optimal even among quantum algorithms. But our lower bound only holds when n is larger than 1 by epsilon to the 4. So there still is this very important question of what is the correct quantum complexity in this region. It would be very interesting to close it. We think it should be the same as the randomized setting, and the deterministic setting, it should be, there should not be any speed up, but we weren't able to prove this. And I'll talk more about this open question at the end. Right, so to recap, we were working in the setting where we have a guarantee of just the Lipschitzness. The oracle was giving us the function value and the gradient, and we were required to output an epsilon optimal point. And we showed a randomized and quantum lower bound for this. In a follow-up work, we had results that extended this, or were at least in a related setting. And that's what I'll talk about now. So there's a related setting for every p, for every natural number p. So let's fix a natural number p, and let's talk about what that related setting is. So the promise is, again, it starts with the same thing, that f is convex. But now you have a higher order promise. You're told that your function is p times differentiable, and its pth derivatives are Lipschitz. So that means that if you have x and y that are close together, then the pth derivative of f at x and at y are also close together. And so it's standard to use the constant LP, although it might be confusing, I've been informed. And we're given query access to f in the sense that on an input x, you're given the function value and you're given all the derivatives, the p higher order derivatives of f at that point x. And this might be a bit far-fetched because these higher order derivatives are huge tensors that might be messy, but we're only interested in how many queries it takes. We don't care about how complex it is to actually give you these higher order derivatives. And this is still an interesting setting, mainly because you do get better algorithms in this setting. So for instance, in the setting with p equals to 1, you get an upper bound of square root 1 by epsilon instead of 1 by epsilon square. So just to recap, so in the setting of gradient descent, our promise on the function f was a p equal to 0 promise, and our query access was a p equal to 1 query access. So it doesn't really fall into, gradient descent doesn't fall into any of these settings of p. But when you set p equal to 1, you get a better algorithm of square root 1 by epsilon. When you set p equal to 2, you get even better. You can get cube root of 1 by epsilon, and that has been improved to 3.5th root of 1 by epsilon. And this turns out to be optimal. No deterministic algorithm can do better than 3.5th root. But it's not known whether it's optimal for randomized algorithms as well. There was a polynomial gap in the randomized lower bound and the upper bound. And in the general setting, when p is even larger than 2, there's an even better algorithm of 3p plus 1 by 2th root, which is really messy, but we won't really need to care about this much. So all that you need to know is that this was also shown to be optimal. The lower bounds from the p equal to 2 setting were actually general for all p. So there was a 3p plus 1 by 2th root lower bound for deterministic algorithms, and a 5p plus 1 by 2th root lower bound for randomized algorithms. And so the question that we addressed was, what is the quantum complexity of all these tasks for all these higher order settings? And what we showed was that it doesn't matter if you have randomized or quantum algorithms, they cannot do any better than deterministic algorithms. We show a lower bound for quantum algorithms that matches the upper bound for deterministic algorithms. Yeah, so we show, that's basically, those are our results in the higher order convex optimization setting. And so now I'll be going through our proofs of the lower bounds, for starting off with our lower bound against the gradient descent setting, and then with the higher order settings. And before that, if there are any questions, I'll take them now.
Can I ask another question?
Sure.
This is all for optimization over the L2 ball, right?
Yes, this is all over the L2 ball. Yes.
Like, can you prove anything for, let's say, optimization over other things like the L1 ball, which you would have in Lasso and other common machine learning problems? How specific is it that you have the L2 ball here?
No, these were, so the dependency of the dimension changes a lot depending on what type of ball you're choosing. I don't currently recall if the general lower bound for the dimension independent setting changes or not if you choose a different type of ball. Mm-hmm. Yeah, I'll have to think about it. I can't say that these carry over.
Thanks.
All right, so Our lower bounds, all of them use pretty much the same kind of functions. So let's introduce those functions. So we start off in an n-dimensional space where we choose vectors v1 to vk to be randomly chosen orthonormal vectors. It's like we've chosen a new basis of r to the n, a randomly chosen basis, and then we're just taking the first k vectors in that basis. And let's assume for now that n is, say, k to the 4 along with some log factors, so k to the 4 log square k or something like that. And the function we're interested in, or the function, one important function is this function, which is asking in our new basis, among our first k coordinates, which coordinate, what is the maximum coordinate, what is the maximum entry in the first k coordinates? So what is the maximum of v1 inner product x, v2 inner product x, and so on until vk inner product x? And the property that really helps us is the concentration of mass in the unit ball around the equator. So it says that if you take a random basis for r to the n, then it doesn't matter which point x you take. So let's first fix a point x, then let's choose a random basis for r to the n. Then with really high probability, each of the entries of our vector in this new basis is going to be really small. It's going to be around square root 1 by n. So that's for all coordinates, the entry in that coordinate is at most 10 times square root log n by n, with probability 1 minus small o1. And why is that helpful for us? Well, because if we look at this problem, what it's saying is that when I make my first query here, since I don't know what v1 to vk are, with high probability, all of these entries are going to be really small. They're all going to be like 1 by k squared. And the actual minimum value that this function takes is minus 1 by square root k. So if I take x equal to minus 1 by square root k times summation vi, this is a vector of length 1. And according to, for this vector, all of these entries are minus 1 by square root k. This is the best that you can do. The maximum value is minus 1 by square root k with this input. So the minimum value of the function in the unit ball is minus 1 by square root k. And if we set our epsilon to be 1 by 2 square root k, then the task is really simple. We want to find an x such that each of these is actually at most minus 1 by 2 square root k. If we find such an x, we have solved the task. If we haven't found such an x, we have not solved the task. And when we make our first query, as I mentioned, all our values are going to be really small. So our first query for sure isn't going to be satisfying this property. And in our first query, the maximum is going to happen at some vi inner product x. So let's assume that our maximum occurs at the ith entry. So the function oracle, it gives us the value of vi inner product x, and it also gives us the vector vi as the gradient, because this is a maximum of planes. And it's basically saying that x has landed on the ith plane, which means that, ignoring boundary conditions, it means that that point and an infinitesimally small ball around it, all of them are basically the ith plane. So our function oracle is just going to return information about the ith plane. It's not going to tell us anything about the other planes. So in our first query, we've learned one of the VIs. We would want to say that in our second query, we can set vi inner product x to whatever value we want because we know vi, but all the other entries are still going to be around 1 by k squared. And so we'll learn one more vector in our second query, and then another vector in the third query, and so on. And even after k minus 1 queries, we want to say that the last vector that we haven't learned, it's, let's suppose it's k, vk inner product x is going to be at most 1 by k squared. So we really do need k queries in order to learn all k coordinates and to output an epsilon optimal point. This is how we want the argument to go, and it's probably how the argument actually works in the randomized case, but it's not easy to make this a quantum lower bound. So to make it a quantum lower bound, we do need to change the function a bit. We don't know what the quantum complexity of optimizing this simple function class is. And that's a very big open question to us. So I'll now describe the changes that we have to make. It's a very simple change, and it dates back to, again, the 80s. So in the second entry, we subtract a quantity gamma. In the third entry, we subtract 2 gamma. In the fourth entry, we subtract 3 gamma, and so on, where gamma is this quantity that's 10 divided by k squared. Right, so this quantity is so small that it really doesn't change the behavior of the function. The minimum value that the function takes is still around -1 by square root k minus some smaller order term, because even k times gamma is a really small term. So if we set epsilon to be 1 by 2 square root k, we're still solving the same task. We still want an x for which each vi inner product x is smaller than -1 by 2 square root k. But the reason this change helps so much is that we're going to start to learn these vectors in order. So in our first query, as before, each of these inner products is going to be at most 1 by k squared. But this minus gamma is going to make all the difference, since minus gamma is subtracting 10 by k squared. So with high probability, our first entry is going to be larger than our second entry by around 10 by k squared, which is going to be larger than the third entry by around 10 by k squared, and so on. So it's going to be in decreasing order. So with high probability, we're just going to learn V1 in the first query. And then now that we know V1, we will be able to set V1 inner product X. And in our second query, we're going to learn V2. And since we're learning things in order, we can't have those weird quantum algorithms that, somehow do a superposition and learn a little bit about each VI and somehow, I don't know, the quantum magic, which somehow does Bernstein-Vazirani, doesn't really work in this case. And we can prove that formally, and we'll do that in a little bit. And to prove it formally, we use the hybrid argument. For this, we have to define these intermediate functions, which just take the maximum of the first I terms. And these intermediate functions have a very nice property. If you fix any setting of your first I minus 1 vectors, any setting of V1 to Vi minus 1, then it doesn't matter what your next query is. With high probability over the remaining unknown vectors of Vi onwards, the probability that the maximum, so let's just write that here. So the actual function f, pen is not too good, is the maximum over this V1 inner product X, so on till Vk inner product X minus gamma. Where's minus? So with high probability, the claim is that the value of the function and the value of this intermediate function is going to be the same. And that's because even though we know the first I minus 1 terms and we can set all these terms as we want, these remaining terms are going to be in decreasing order, starting from Vi to Vk. So the maximum is either going to be in the first I minus 1 coordinates, or it's going to be the ith coordinate. It's definitely, with very low probability, it's going to be a coordinate after the ith coordinate. So with high probability, our function, we can't really differentiate between the function f and this intermediate function. And how we use that is in this way. So this first line here is just the run of a standard query algorithm. You start with some initial state. That it could be just the all zero state, since you're applying a unitary here. And then you're calling the oracle on the resulting state. Then you're doing another unitary, you're calling an oracle, another unitary. This is the general format of any k-1 query quantum algorithm. And then you do a measurement at the end. And based on that measurement, you output an answer. Now, as far as the first query is concerned, let's look at this actual run of the algorithm and this corrupted run of the algorithm, or a hybrid run of the algorithm. So in this hybrid run, we've replaced one call of the oracle to a call to the oracle that only has the first entry. It's just the maximum of the first entry. So in these two runs, the state is exactly the same before the oracle call. And with high probability, we can't tell whether you call the actual oracle f for f or the oracle for f less than or equal to 1 by this above property. So after this oracle call, the two states are approximately the same. And after that, we're running the same unitary on both of the states. So by unitarity, the ending state of the actual run and this once corrupted run are approximately the same. Now, let's compare this once corrupted run with a twice corrupted run. So in this twice corrupted run, we've corrupted the first oracle call and the second oracle call. And in this case, we've called the same oracles up till here, right? And all these oracles only had access to V1. So at this point, the state that we have is truly independent of V2 and V3 and so on. And since it's truly independent of V2 and so on, these two states are going to be approximately the same because the input state to this oracle had no dependence on V2 apart from the fact that it was orthogonal to V1. So again, we can say that the ending state of this once corrupted and twice corrupted runs are approximately the same. And this argument can continue, and our conclusion eventually will be that the ending state of this completely corrupted run and the ending state of our actual uncorrupted run of the algorithm are close to each other. And this completely corrupted run has only had access to oracles that were independent of VK. So the ending state of this last run is truly independent of VK. And so it's not possible for this to have output a correct answer except with low probability. So this finally completely corrupted run is going to fail. We can guarantee that with high probability. And so therefore our initial uncorrupted run will also fail. Not the best presentation of the hybrid argument, but I hope that was understandable. So that's basically the lower bound now. You need k queries. This proves that no k-1 query algorithm can succeed on a random setting of v1 to vk. And so we have a lower bound of k. And since epsilon was set to 1 by 2 square root, since epsilon was set to 1 by 2 square root k, that means that k is 1 by 4 epsilon square. We could improve that constant 4 to anything larger than 1. And we chose n to be k to the 4 log square k in our argument, which corresponds to around 1 by epsilon to the 8. But we didn't actually need n to be that large. This whole argument would have worked as is, with n being something like k cubed times log square k, and gamma being k to the minus 3 by 2 instead of k to the minus 2. And if you follow the parameters here, this brings n down to 1 by epsilon to the 6. Now, we claimed in the graph at the beginning that we had our lower bound of 1 by epsilon square when n was larger than 1 by epsilon to the 4. Now, that is a complicated argument, which uses a very clever modification from a paper of Bubeck, Zhang, Li, and Sidford, using something called the wall function. And using that, n can actually be brought down to 1 by epsilon to the 4. And that's the state of the art right now. I can't explain the wall modification. That's, I mean, it's really cool. You should see it from their paper or from our paper, but I can't explain it. Yeah. So that's it for the lower bound in the gradient descent setting. Now I'll be moving on to the higher order convex optimization setting. But it basically, it uses the same function as the base. Right? So our goal is now, we want a class of highly smooth functions. We had just a maximum of various planes, which wasn't even differentiable. But now we want a class of highly smooth functions. And our plan is that we're going to just create a smooth version of what we used previously. The hope is that just by taking the non-smooth versions and smoothing it out, you wouldn't have changed it much. And so it should retain the property that you will learn the vectors one at a time. And so you need a lower bound of k for optimizing with the same epsilon. And the only problem with this is that if you're actually taking a non-smooth function, just a maximum of 2 planes, and you're just smoothing it out in a small region, this is going to make the higher order derivatives very large. Because here the gradient is going from, say, -1 to 1 in a very small region. So that means that the gradient has changed very quickly. So that means the second gradient must have been really large. And for the second gradient to have become so large from 0, the third gradient must be even larger, and so on. So when you do this, it's very natural for these larger order derivatives to become really large. And if we can manage this while limiting how large these larger order derivatives become, if we can just keep it to within k to the 3p by 2, then we would get exactly the lower bound that we wanted, because LP by epsilon would then become k to the 3p by 2 times square root k. And our lower bound is k. So that would give us exactly a 3p plus 1 by 2th root of LP by epsilon. And so this is actually what we're going to achieve. But just to keep an easier picture of things in mind, recall that gamma was set to k to the -3 by 2 in our previous lower bound. And so what we're really going to do is we're going to show that we can do this with LP being gamma to the -p. So we don't need to keep these nasty fractions in mind. Just we want something that looks like gamma to the -p for our LP constant. All right. So let's do that smoothing. So to start with, we'll see the simplest type of smoothing. Here is a place where 2 of our planes meet. And what we're going to do is we're going to convolve this function with a ball of a small radius. So the smoothened function here, S of f, S of f at a point x, it's basically you're taking a ball of radius eta around x and you're averaging the function in that ball. And this changes the function only in a small area here. And that's fine, because what we said was that V1 inner product x is going to be the maximum in our first query. In fact, it's going to be around gamma larger than V2 inner product x minus gamma. So that means that our first query is actually happening somewhere to this side, right? Where the distance of this from this point where the 2 planes meet is something like gamma. So it's got a fair distance. Our first query is always landing far away from the points where these meet. So if you do this convolution, our first query is not even going to notice that the function has changed. It's still only going to learn V1. It has no idea. Nothing about V2 has seeped into the first query. And this is exactly what I said. If eta is much smaller than gamma, then the lower bound still holds. And a really nice property of the smoothing is that it always adds an extra level of differentiability. If your function was thrice differentiable, but not 4 times differentiable, and you do the smoothing, it becomes 4 times differentiable. So that means one obvious thing to try right now is to just use this smoothing p times on our initial function. It becomes p times differentiable. And we'll want our ball to be of radius, say, gamma by 100p or something like that. So that even if you've convolved it p times with such a small radius, you still haven't corrupted any place where the first query is going to happen. The problem with this strategy is that if your function has parameter LP, but is not p plus 1 times differentiable, and you smooth it, then the parameter LP plus 1 of the smoothened function, it's going to be at the best bound you can give on it is LP times n by eta. So that means that if you start with something which had L0 Lipschitz promise of 1, then after smoothing it p times, you have LP is at most n to the p by eta to the p. And if it was just 1 by eta to the p, that would be great, because eta was something like gamma by 100p. So if it was just 1 by eta to the p, we would be getting gamma to the minus p times, say, 100p to the p. Now 100p to the p, we'll treat it as a constant. So we only care about dependencies on things other than p. So that would have given us gamma to the minus p, except for this n to the p term that has come in here. And unfortunately, n is like, in our setting, n is approximately gamma cubed or so. So that spoils our lower bound. It still does give us a polynomially loose lower bound. So this simple smoothing by itself does give us the fact that you don't get an exponential speed up for the quantum setting, but it doesn't give us the tight lower bound that we wanted. All right, so the smoothing hasn't worked for us, but it still is going to be useful. So let's mention some useful facts about this. It retains smoothness of the original function. So if your original function f has some parameter LP in it for its pth derivatives, then even after you smooth it, the pth derivatives of the new function are also LP smooth. And also it's a linear operator. The smoothing of f plus g is just the smoothing of f plus the smoothing of g. Actually, I want to talk a little bit more about this part. So I said, if our eta is really small, it changes the function only in a small strip. There's something that's more that we can say than this. So let's take this picture here. So what this was saying was that if I take some point here and I average it in a ball of radius eta, its value doesn't change because it's just it's averaging a plane in a ball. So it's just going to be the same as the value at the middle. However, if this function wasn't a plane, if it wasn't the maximum of two planes, if say you had some weird function like this, which is maximum of this red curve and this blue curve, and we took, again, we did the smoothing at this point. So the value at this point of the new smoothed function, it's going to be the average in a ball around that point. It's not going to be the same as the value of the original function. But an important point is that it still only depends on V1. It's still only a function of the red curve. And that's good enough for our lower bound. It's only telling us about V1. It's not leaking any information about V2. It's only when you take the average of some point here that some information has leaked about V2 because we're also averaging some points of the blue plane. It's not just the red plane. So although I've stated it as it only changes the function in a small strip, what I really mean here is that the dependency of the answer only changes in a small strip. It still depends only on V1. That's going to be important. But yeah, so the second ingredient that we need for our smoothing, for our lower bound to work, is the softmax function. And this is a beautiful approximation of the max function. So ignoring this parameter rho for now, what it's doing is it's taking the exponents of the arguments to it, it's adding them up, and then it's taking the log of that. So suppose you were trying to compute the softmax of say A and B. Let's assume rho is set to 1. And let's assume that A is larger than B by some box. So A is B plus box. So then this becomes e to the A. So we're taking log of e to the A plus e to the B, which is e to the A plus times 1 plus e to the minus box. So this is the value of the softmax, which is actually equal to A plus log of 1 plus e to the minus box. And 1 plus e to the minus box can be approximated to, assuming that box is large enough, this is going to look like A plus just e to the minus box. In fact, this is a good approximation anytime, I think. Yeah. So it looks, so the softmax is computing pretty much just the maximum plus this exponentially small constant seeps in. The point of rho over here in this whole thing is that if box is not small enough, then by setting rho, what you're effectively doing is you're changing this e to the minus box dependency to e to the minus box divided by rho. So if I make rho really small, it's going to make e to the minus box by rho really exponentially small. So that's the whole point of the parameter rho. So let's look at this in practice. So this is just the maximum of the two planes, and the purple curve is the softmax of them. This is with the parameter rho is equal to 0.5. And if you make rho smaller, it's going to become exponentially small much faster. And the way we're going to use, so first, some properties of softmax is that it's convex, which is good, and that it's infinitely differentiable, and it has a nice dependence on rho. So it's the softmax's LP constant is rho to the minus p. It's really good that everything is looking like something to the minus p, because that's exactly what we needed. The problem with softmax is that if you take any point, even if you take the place where the first query was happening and you query the softmax at that point, you're getting the purple answer, which is slightly smaller, slightly larger than the red answer. So it is actually leaking some information about V2. And that's exactly what we didn't want. So using softmax, it seems like it completely decimates our lower bound approach. But there is still a way to use it such that it doesn't do that. And so for that, let's set rho to be much smaller than gamma. So say gamma by 10p log n. So this means that in the places where the first query is happening, since the red plane is omega gamma larger than the blue plane, the purple value is very slightly smaller, very slightly larger than the red plane. So it's just like n to the minus 4p larger than the actual value of V1 inner product x. And we're going to use this fact by making this change. So I'm taking the maximum of the red plane and of the softmax function, except the softmax function, I've subtracted a very small quantity from it. So I've subtracted n to the minus 2p from it. Now I've subtracted a very small amount, but that's still enough for the red plane to become larger. So where our first query was happening, the red plane is actually larger. So if I make the query to this maximum of these two things, I'm actually getting just the value of V1 inner product x. It has successfully hidden V2. The only problem, and the thing that sounds like a major problem, is that this function is no longer smooth. And we wanted to make the function smooth. But it's very close to being smooth. So this function, it's actually just the same as the softmax function plus this correction. And when the softmax function is actually larger, the correction is 0 because you don't need to correct it. And when the red plane is actually larger, the correction is a very small constant. I mean, it's something that goes to 0, but it's really small. And you can use properties of softmax and prove that this correction actually has a very small L0 constant. So now what we're going to do is we're going to take this non-smooth function and we're going to smooth this p times. And since smoothing is a linear operator, it's going to be the same as the smoothing of the softmax function plus the smoothing of this correction. Now the smoothing of the softmax function, it's going to keep the same LP constant. It's going to be around rho to the minus p. The smoothing of the non-smooth part, well, that's going to be L0. Now L0 constant of this was n to the minus 2p. It's going to be the L0 term times n by eta to the p. Now n to the minus 2p is going to completely swallow this whole thing is basically 0. The LP constant of the smoothing of the non-smooth part is approximately 0 because n to the minus 2p is completely canceling out n to the p and eta to the p. And so we finally managed to come up with a function such that its LP constant is approximately rho to the p, which is going to look like gamma to the p, rho to the minus p, which is approximately gamma to the minus p. And I mean, I suppose you really have to take another look at it, but it also has this hybrid property that in our first query, you're only going to learn about V1. In our second query, you're going to learn about V2 and so on. So I'll just show what the actual final function looks like. I'll just skip over the calculation here. So yeah, basically LP is around k to the, it's around gamma to the minus p times log n to the p, which gives us our lower bound of 3p plus 1 by 2th root times some log factor. And this is what our final function class looks like. So you're taking the maximum of just the softmax of the first term, which is just the same as the first term, then the softmax of the second term minus a small value, the softmax of the first three terms minus, again, twice the small value, and so on. Right, so if you look at what this maximum looks like, it would be, if you go through the calculations, you'll see that on your first query, V1 inner product X is around gamma larger than the second term. So this is going to be the maximum. In your second query, this is going to be the maximum with high probability, and so on. And then you're convolving it P times to make sure that it's finally smooth overall. It's quite ugly, but it works. So that's really all I had to say about our coming up with the lower bounds. I would be going on to open problems next, but I feel like there could be a lot of clarifications that are needed. So I'll stop here for questions for now.
You still have about 10 minutes. So if you want to discuss the open problems and then go for questions, that's also fine.
All right, sure. So, all right, so our open problems are basically things that we've come across. So what is the complexity of optimizing this function class where we don't have these minus gammas to enforce the order of learning the VIs? In fact, the setting that is quite interesting to us is where k is actually equal to n. So we're basically taking a new basis for our r to the n, and we're asking what is the maximum coordinate. We can show that for randomized algorithms, this requires omega n queries. And that's what gives us the complete tightness of gradient descent as soon as it becomes more optimal than center of gravity. We can't prove the same lower bound for quantum. We don't even know if it holds, and that's what this open problem is. Another interesting open problem is, what if your functions are highly smooth, but your oracle is only giving you the first two, the function value and the gradient value? So clearly our lower bound is still going to work, but there might be a better lower bound, or there might be a better upper bound. It's not clear. And this is an interesting question to study even in the classical setting. People have not really studied this setting. And another more philosophical question is, so one way we came across this lower bound is because we wanted it to work for quantum algorithms. So we had to use the hybrid argument. We wanted to make sure that everything is being learned in order. That's why we went through the trouble of ensuring that the softmax is decreased a little bit and so on. And that happened to work out, and it gave us an optimal lower bound. And if we were trying just for a randomized lower bound, it's quite likely that we would not have stuck so strongly to techniques that work against the hybrid argument. And we might not have actually come up with this lower bound. So by having our hands tied, nature led us to an actual fact of convex optimization. So are there other areas where we can perhaps come up with good lower bounds using the hybrid argument? It's a very vague question, but yeah. So actually, I'll just take a few more minutes. So regarding this first open question, suppose you're told that V1, so we're adding an additional promise here that either V1 is equal to E1 or minus E1. Right? So each VI, you're promised that it's either the ith basis vector or the negative of that. So in this setting, we can still prove an omega n lower bound for randomized algorithms. It's quite simple if you analyze how this function behaves. But there is a quantum upper bound of square root n queries. If you're given this extra promise, then using Belov's algorithm, you can solve this function class in square root n queries. So there clearly are interesting cases where quantum does do better than classical. So one open problem could be, are there general classes of convex optimization problems that maybe some reasonable restriction you can keep on what your convex optimization problem looks like, such that there is a speed up for quantum algorithms. I guess, yeah, those were my problems. Anything else? All right, yeah.
Any questions? Okay. Let's then thank Suhail. Thank you, Suhail. It was a really nice talk. Oh, yeah, sure.
Can I ask a question?
Sure.
So thanks for the nice talk. So what I understand is that you've now looked at, let's say, the non-smooth case and the smooth case for gradient descent. I guess the next natural question would be to also assume instead of only an upper bound on the Hessian, also a lower bound. So about the strongly convex setting. Have you thought about this setting at all?
No, we've not. We've not thought of this strongly convex setting. One direction which we had looked at was quadratic programming. We think there are very interesting open problems there as well, but we kind of got sidetracked and went to the highly smooth setting after that, so we didn't give it too much thought.
So for quadratic programming, you mean still the convex case?
Yeah. So.
And then also with a lower bound on the Hessian or not? Because I think that's actually the setting I'm interested in. So just if you have a quadratic given by a positive definite matrix.
Yeah.
That's the setting you're looking at.
The setting was you're given. So I think it was something like finding the smallest eigenvector. Wait, it's been a while. You're given a matrix M and you're trying to minimize X transpose. There was some condition on the condition number was bounded of M. Okay. I believe that's.
And there you could show speed ups or not?
Oh no, we didn't actually manage to show anything there. It's a good direction to go.
Can I still ask a general question, Suhail?
Yes.
So the result sounds extremely general and also extremely damaging, as if it sort of precludes all quantum speedups for convex optimization. And yet there's like a sort of steady flow of papers that give polynomial speedups to all sorts of variants of convex optimization. Like how can these two things be reconciled with each other? Like what are you sort of not including in your general lower bounds?
So here we were able to embed like a lot of structure where this function had parts that just didn't depend on each other. And then, like for instance, the very fact that quantum can do gradient much easier, it can find out the gradient just given function value queries. So that's a Bernstein-Vazirani like argument. So it's like you have a linear, you have a vector G and you're getting values of G inner product X. And you're trying to recover X from that. So it doesn't matter what X you query, you're always getting some information about all of G, so to speak. You can't embed a modular problem into that problem. So this had parts which depended only on V1 or only on V2 or only on V3. But I think perhaps the classes of convex programming where quantum does find a speedup is constrained to not allow such modularity, I guess. Perhaps our setting is general enough that it's, yeah, okay, yeah. I don't have a very clear answer on this, but yeah, the feeling that I get is that this is more, you can embed combinatorial problems into this, where it's much harder to embed combinatorial problems into the others.
So given this result, would your advice be for people to stop working on quantum algorithms for convex optimization, or? Kind of a
For
provocative
general
answer.
convex optimization, perhaps.
I see.
Well, but again, so this is an interesting question that had come up in the previous talk, which is how representative is this of problems that pop up in convex optimization? Do you actually have like maximum of planes popping up? And I asked this to some people who are more well-versed with optimization literature, and they didn't really have a clear answer on that.
I see. So maybe speedups can be found by looking at sort of specific objective functions that actually occur in reasonable optimization. Okay, yeah, that's good.
Perhaps. Yeah.
Thanks.
So I had one small last question. So this hybrid argument, I think it's very nice. I also have one other setting where I'd like to try it. So there is sort of okay. So somehow the point there is like I know a classical lower bound in this setting, and with every query that I make to a complex function, I can only eliminate sort of a small subset of possible sort of functions in the family. So do you think sort of this would generally work? Like, is this sort of enough to do this hybrid argument, or?
Well, if each query is eliminating a different set of, so I mean, you're saying your first query eliminates a small set of points. But is it really that there exists a small set of points that are eliminated by any first query, or that for any first query there exists a small set of points that are eliminated? So is there like a global set of points that you're eliminating in your first query?
Yes, I'm eliminating a global set of points in my first query.
Right. So the set of points that you're eliminating doesn't really depend on the query. Or with high probability here.
That is a good question. Okay, I'm not sure how to answer this right now. Anyway, I'll think about it and maybe email you.
So in this case, we're always finding out V1. We're eliminating all other possibilities in the first query. And that was very important. If your first query could, with some probability, be eliminating V1 or with some probability eliminating V2, then it's really hard to make that a quantum lower bound. And sometimes it just, maybe there is a better quantum algorithm. For instance, when you set V1 is E1 or minus E1, the proof that this requires omega n queries for randomized algorithms, it's basically saying that each query is only learning at most 2 of the values. So you need like n by 2 queries to learn all n values. But you still have a better quantum upper bound despite that.
Yeah. Okay, thank you.
Yeah.